All right, classes, let's do a quick rundown of some of our notes that we had this week. A couple of things that we saw. If you look at our board notes from Wednesday, so let's get the highlighter tool going. And Wednesday, November 6th, we had some physics notes on friction. So in Boys in the Boat, we talked about physics connections, why particularly friction, and why physics at all. Well, in this class, we have a little bit on the way of engineering standards. And if you check out the engineering standards, the best way to go through some of the things that you'll see in high school are Newton's laws. If you check out Newton's laws, numbers 1, 2, and 3, of course, those are the things that we are talking about in terms of the Boys in the Boat. You might remember too, hopefully you do, that when we saw, we use a different color pen here, a little bit on the spaceship, kind of the spaceship that had the big spinning wheels in it that was returning from Mars. When you're talking about any kind of travel between planets, you're talking about a spaceship that once it gets the initial push off the planet, doesn't need to spend that much fuel because of Newton's first law, which is inertia. You've got the inertial law carrying it through space without worrying about friction because there's a near vacuum in space. There's not too much air to run into out there. And then when you're looking at, let's go back to the highlight tool here, friction is a force that opposes motion. You notice I was using a little arrow down here. And when we're showing forces, and this is force equals mass times acceleration, when we're using forces, we always represent forces in physics, or almost always, with an arrow. And the reason I love that, by the way, is just it was visually for me, I liked it when I was learning physics because the size of the arrow represents the direction and the magnitude or the size of the force. So it was a really nice visual for how you understand different forces and how they interact. Okay, moving on, we checked out the forces of flight a couple of times in here, and we also revisit those when the scientists visit us one of these days this year. They're going to do the old paper airplane experiment where we check out variables, how we change the ailerons, popularly known as the flaps on a plane, and how it will affect the flight. And check out, let's try a different color highlighter here just to try and make it stand out. If you look at, we use these subscripts right here. So you've got F subscript L for lift, F subscript T for thrust, and of course in almost every free body diagram, which is what this is, you've got an arrow for gravity, and then F subscript F for friction or drag. And then drag, of course, is one of those things that we talked about. Let me use this tool here just to make it a little big or smaller so I can use a little more space to draw. Check out this part, which I think is fascinating. When you drive a car and you're talking about friction, the amount of friction, so you've got your bad picture of a car right here. I'll try and draw one best I can quickly with this little drawing tool. But as you're cruising down the freeway, you're running into air molecules, of course, and there's also friction with the ground. And as the car goes faster and faster, so if you graph speed along one axis, or velocity I should say, but speed along one axis and friction along the other, it doesn't go up in a straight line like this. Instead, let's choose a different color just to make it stand out a little bit. It goes up in sort of a curved line, and it means that the faster you're going in the car, the more and more friction is holding you back. So when you see someone speeding on the freeway, not only is it dangerous, not only is it not good driving practices, and you're decreasing stopping distance if you're following too close and all those things, but you're wasting money. If you look at how much more energy it takes to get a car to go really fast, as you go past 65, 75 miles an hour, like I see on Highway 280 all the time, you're wasting a lot of money by going too fast because you're trying to push a car faster, but you're getting diminishing returns. On the next slide, let's get it here, we were trying to show with some free body diagram the Boys in the Boat. And again, we had a picture of the boat moving here. This is the coxswain, of course, and the direction of travel. They're trying to get the boat, let's try a different color right here, to move in that direction right there. And when you've got this direction of travel, you've got a lot of things that you can see in the video. For example, the oar itself is a lever. Yeah, let's get that and use the proper tool. So it's a lever arm. And when we work on human body systems, the skeleton is a series of levers held together by ligaments, so that's a nice little tie-in there. Also, when we're looking at, let's try a different color just for fun, cells. We know that we are eukaryotic cells. We have an organelle called mitochondria. That's the powerhouse of the cells, and each of these rowers is having to use oxygen to go through glycolysis to turn sugar into energy. And the molecule that does that, hopefully you guys remember, is good old ATP. We've been learning about that all week, adenosine triphosphate. It's sort of like the energy currency of a cell. Finally, the last thing, sneaking in the most important subject, in my opinion, of the entire year, and it's really what we've been leading up to. This sneaks in evolution. We had an opportunity to talk about prokaryotic, those are cells without a nucleus, and eukaryotic cells. And in The Boys in the Boat, one of the members, and we'll see it, the stroke seat, guy by the name of Don Hume, right here, ends up getting a terrible lung infection, most likely a bacterial infection, although they can be caused by viruses as well. And this leads us to where we're going with understanding evolution, because look at the year. The year that this is taking place, especially when he gets this bad lung infection, is 1936. There are no antibiotics on the scene yet. Antibiotics didn't make the scene really until the end of World War II, around 1945. And when you're checking out the World War II, 1945 application of antibiotics, we're talking about a medicine derived from a fungus that has saved millions of lives, but at the same time, the overuse of antibiotics is causing a little bit of a problem, because antibiotics can reproduce in as fast as 20 minutes. And we're going to learn as we go forward and learn about evolution, how overusing antibiotics allows them to adapt. And so if you have, and this is getting way ahead of ourselves, but let's just check it out. If you have an antibiotic that kills just about every bacteria, except maybe one that might have what we're going to learn about is called a mutation that can survive a particular antibiotic, that one can then go on to reproduce. And again, look at the reproduction time in a bacteria, 20 minutes. That's really, really fast. Highlight that just a little bit more. And that means that bacteria are learning to get around penicillin and the antibiotics we throw at them. So threw a lot at you, but I just wanted to go through our notes, how we're combining a little bit of physics and a little bit of chemistry and biology here. Take care, and I will see you guys out there online.